Hello everybody, this is Dr.Nageswara, Assistant Professor of Physics, SRR and CBR Government Degree College, Autonomous, Vijayawada. Today we will discuss one of the method to produce low temperature physics is Joule-Kelvin effect. In the previous class, we discussed that there are different methods to produce low temperatures. The first method is freezing mixtures. By using that, we can produce temperatures up to minus 80 degrees Celsius. The second method is a Joule-Kelvin effect, and the third method is adiabatic demagnetization. Today, we will discuss about Joule-Kelvin effect. This is also called Joule-Thomson effect. According to Joule-Kelvin, when the real gas which is passing through the porous plug from high pressure region into the low pressure region, whose temperature changes. This was discovered by Joule and Thomson. So this is called Joule-Thomson effect, or also called Joule-Kelvin effect. You see here, this is the porous material. So this is the cylinder. It is divided by this porous material into the two compartments. This is compartment 1. This is compartment 2. Where the first compartment is filled with the gas whose pressure is P1 and volume is V1. And the second compartment having pressure is P2 and volume is V2. This is divided by two pistons. This is A piston, this is B piston. So when we move this piston A towards right side, whose pressure increases, then the gas which is in the compartment 1 is passing through the porous material and entered into the compartment 2. So here P1 and V1 are pressure and volume, and P2 and V2 are pressure and volume in compartment 2. If this piston P1 is pushed towards right side, the gas is pushed through porous material and entered into the second region. So that due to this expansion, the temperature changes. This is called Joule-Thomson effect or Joule-Kelvin effect. Using this experiment, Joule and Thomson observed that all the gases except hydrogen and helium shows cooling effect. But all the gases, including hydrogen, helium, shows change in temperature. So the first point observed by them is when the gas is passing through the porous plug from high pressure region into the low pressure region, the temperature changes. The observed by them is, second point is, except hydrogen, helium and neon gases, all the gases at room temperature shows cooling effect. Is nothing but due to this natural expansion, the temperature of all gases decreases. But those gases, that is hydrogen, helium and neon, shows heating effect. Is nothing but when these gases passing from porous plug, whose temperature increases. The change in temperature of this gas is directly proportional to difference between pressures of in the two compartments, that is difference of P1 and P2 at a constant initial temperature. It means that the change in temperature is depending on the initial temperature of the gas in compartment 1. If the initial temperature of the gas is small, the effect of cooling is more. At such one of the temperature, when the temperature of the gas at compartment 1 increases, at one of the temperature, that gas shows heating effect. This initial temperature is called inversion temperature. So all the gases whose inversion temperature is more than the room temperature, so that all the gases shows cooling effect when it is passing through the porous plug. But inversion temperature of hydrogen is minus 80 degrees Celsius and helium is minus 240 degrees Celsius. So that whose initial temperature is less than the room temperature. So these two shows the heating effect when passing through the porous plug. If the initial temperature of this hydrogen is less than minus 80 degrees Celsius, when it is passing through the porous plug, it also shows the cooling effect. Similarly, if the initial temperature of the helium is less than minus 240 degrees Celsius, when this helium is passing through the porous plug, It also shows the cooling effect. That is the importance of the inversion temperature. So in these cases, in compartment 1, the amount of work, external work, is done on the gas by the piston. And here in this compartment 2, the gas is done on the piston. Not only this external force, some internal force is also existed, which opposes the attractive force between molecules in the gas. So that plays major role in the cooling effect. So to derive the relation for how much quantity of temperature is decreasing, we are taking, there is two pistons and B whose pressure and volume are P1 and V1 in compartment 1, and P2 and V2 are pressure and volume at compartment 2. Now when this piston is pushed gas towards the porous plug, some external work is done on the gas. So we know according to the work dW is equal to PdV. According to the thermodynamics, amount of work done is equal to pressure P into change in volume. Now the work done on the gas is P1 V1, because actually V1 is, that is a difference in volume, that is P1 V1. Similarly, in the second compartment, the work done by the gas on the piston is P2 V2. So the net external work, this is these two are external works. So the next external work done by the gas is P2 V2 minus P1 V1. Not only this external work, some internal work is also done in between attractive force of molecules in the gas. So what is this quantity of this internal force or internal work? So we assume that according to the, for the real gases, according to van der Waals gas equation, that is P plus A by V square into V minus B is equal to RT. In the pressure term, there is a P plus A by V square. A by V square shows the internal work done per unit area. That is excess pressure. Due to this excess pressure as attractive, this is attractive force, some internal work is also done. How much is done? That work is can be written as, internal work can be written as A by V square into dV, because the excess pressure A by V square is P is equal to A by V square. That is that the total internal work done is equal to integration P dV, where P is replaced by A by V square, where according to the van der Waals gas equation. So whose volume is changing from V1 to V2, so that lower limit is V1 and higher limit is V2. That is integration V1 to V2 A by V square into dV. Of course, A is constant, V is the volume occupied by the gas. So that is integration dV by V square is minus 1 by V, we know. So that is A into 1 by V1 minus 1 by V2 after submitting these values, limits. Now the total work done by the gas is external work done plus internal work done. So that the total work is, external work is P2 V2 minus P1 V1, and plus internal work is A by V1 minus A by V2. Of course, this is taken as equation 1. According to the van der Waals gas equation, already we discussed earlier, that is a P plus A by V square into V minus B is equal to RT, where P and V are pressure and volume, A and B are small constants, R is, we know, universal gas constant, T is absolute temperature. So by expanding this, P into V is PV, A by V square into V is A by V, minus P into B is PB, plus into minus minus A into B by V square, that is equal to RT. But we know A and B are very small constants. So that A and B, A into B is very, very small. For example, if A is equal to 0.1 and B is equal to 0.01, then the A into B is 0.001. So that value is very, very small. And hence, this AB by V square term can be cancelled, maybe neglected. So that equation for real gas, we can write PV plus A by V minus PB is equal to RT, because AB by V square term is neglected. So from this, we may write that PV is equal to RT minus A by V plus BB. So there is two compartments we have. In compartment 1, there is a pressure is P1 and the volume is V1. For that compartment, that real gas equation can be written as P1 V1 is equal to RT minus A by V1 plus P1B. And also in the second compartment, P2 V2 is equal to RT minus A by V2 plus P2B. So now we may write that the total work done, that is the P2 V2 minus P1 V1 is this minus this, that is RT minus A by V2 plus V2B minus RT plus A by V1 plus, and that is minus P1B. Of course, where RT and RT are cancelled each other, so that external work done, that is the P2 V2 minus P1 V1 is equal to A by, that is 1 by V1, that is minus 1 by V2. Here also B, here also B. When minus B is taken as common, that is P1 minus P2. Why it is taken minus is, we know P1 is greater than P2. Because in compartment 1, the pressure is more than the compartment P2. So that we have taken minus is taken as common. So that minus B into P1 minus P2. Now, what is the total work done? So that is the total work done. That is W is equal to, that is from this value, P2, V2 minus P1, V1 is replaced here. That is A by V1, A into 1 by V1 minus 1 by V2 minus B into P1 minus P2 plus already is there A by V1 minus A by V2. Of course, when A is taken as common here, A into 1 by V1 minus 1 by V2. Here also A into 1 by V1 minus 1 by V2. So that the total work done W is equal to 2A into 1 by V1 minus 1 by V2 minus B into P1 minus P2 is already there. Where A by V1 and here A by V2 are very small quantities, and hence we apply for the approximation by using the ideal gas equation. PV is equal to RT, that is 1 by V is equal to actually P1 by RT, PR by RT. From that 1 by V1 is equal to P1 by RT and 1 by V2 is equal to P2 by RT. When these values substitute in the above equation, the total work done W is equal to 2A by 1 by V1 is replaced by P1 by RT and 1 by V2 is replaced by P2 by RT minus B into P1 minus P2. Of course, there is RT and there is RT is taken as common, that is 2A by RT into P1 minus P2 minus B into P1 minus P2. Or of course, here also P1 minus P2, there also P1 minus P2. When P1 minus P2 is taken as common, that is a 2A by RT minus B. So this is total work done by the gas in the porous plug experiment. That is taken as equation 2. But we know the total system, that is a cylinder is thermally insulated. So there is no heat came from outside and there is no heat going outside. So that is adiabatic process. So that the total work done is taken from its internal energy only. So whose temperature decreases by dt, that is taken as minus dt, the fall in temperature, and that is a Cp is a specific heat of that gas at constant pressure, then the amount of work done or maybe amount of heat supplied to restore the original temperature is minus Cp dt. According to the formula, dq is equal to mc dt, specific heat equation. That is, we know specific heat C is equal to 1 by m into dq by dt. That is, dq is equal to mc dt. Of course, m that is taken as 1 mole of gas, m that is maybe taken as equation 1. That's a dq is equal to c dt, where c is Cp, that is minus Cp dt is in calories. Of course, it is in joules, that is in SI system of units, that is multiplied by joule constant J, then the total work done, that maybe the total heat supplied to restore the original temperature is minus Cp dt into J, where J is the joules constant, whose value is, we know, 4.12 joule per calorie. Of course, this equation 3 and equation 2 are common, equal, because this is work done by the gas and this is same as to restore the same original temperature. So when the equations are 2 are compared, that is minus Cp dt J is equal to P1 minus P2 into 2A by RT minus B. From this equation, that is dt is equal to minus of P1 minus E2 by Cpj into 2A by RT minus B, where minus shows the temperature decreases. This is expression for the cooling of gas using this Joule Kelvin effect. So by using this, what can we say? By using this, we can say that at any temperature, the cooling is directly proportional to difference of the pressures, that is P1 minus P2. If P1 minus P2 increases, the change in temperature is also increases. There is nothing but the difference between two pressures are very high. The change in temperature, a cooling effect is also more. The second observation from this experiment is if the T is the initial temperature. If the initial temperature is very less, the difference in temperature is very high. So if the initial temperature is very, very small, the result of cooling effect is shows very high. That is the second observation we observed from the above equation. From this equation, if 2a by RT is equal to B, then 2a by RT is replaced by B minus B is equal to 0, then dt is equal to 0. It is nothing but 2a by RT is equal to B, that dt is equal to 0 is nothing but it shows nothing, no cooling or no heating effect. That is non-heating effect, neither heating effect or not cooling effect. So at this condition, that is T is equal to 2A by RB, that temperature is called inversion temperature. So that is T is equal to 2A by RB is called inversion temperature. So this is depending on constancy and B and R, van der Waals gas equation, gas constant. So depending on this initial temperature, the gas maybe shows heating effect or cooling effect at room temperatures. So this is about the Joule Kelvin effect and whose magnitude, how it will change. Thank you very much. Actually, I am designing to introduce remaining topics in this skill enhancement course, low temperature physics and refrigeration, into PowerPoint presentation videos. So I kindly request you to subscribe for further updates. Thank you very much.